Log on, tune in, find out. Another good idea from Cambridge.
From Lyon, being able to pass by a couple of days and talk on the Pentagram map. That's a new integrable system.
Thank you very much. I'm very pleased to give a talk here. So this is a joint work with Sergei Tabachnikov and Richard Schwartz. And so before I start to talk on serious things, first it's a short quiz. So I will ask you a couple of questions and you will help me, I hope. So let me draw 4 points on the same line, then 2 pencils of straight lines passing through these points. Something like that. And so the question is, what do they have in common, these 2 pencils? Yeah, so it's a question for you, actually. Yes, these 2 pencils of lines, what do they have in common? Well, yes, this is the right answer, but so this is a question number 1. Well, okay, so to warm up. Well, so the answer is actually they are the same. These 2 pencils of straight lines are the same. In which sense? Projectively equivalent. This means if we consider the action of the standard action of GL3, if you prefer projective GL3, then these 4 lines can be sent into these 4 lines. There is an element of a projective transformation that simply sends 1 pencil into the other. What this is due to the fact that the only invariant of 4 lines through 1 point is the famous cross ratio. So here the invariant is the cross ratio. That perhaps I will remind the explicit formula later, but maybe everybody knows it already. Well, okay. Now, the second question. So I started with this blackboard because perhaps I will keep the picture during my talk. So let me draw the most arbitrary pentagon I can draw. Okay, so it is sufficiently arbitrary. Then, so given a pentagon, let us write down draw all the diagonals. And so what we get is another pentagon, a smaller pentagon inside. Question number 2 to everybody: what do they have in common? The exterior pentagon and the smaller pentagon inside. Well, since this is the same question, so same question, same answer. They are, so this was the question answer. That's the answer. They are the same. Well, let me give you the proof, by the way. So let me take, for instance, this vertex of the small pentagon, and let me draw two lines like that. So what do we see? We have this vertex and four lines, and we have this opposite vertex with four lines. And the picture is exactly the same. So, well, and this, well, it is almost the complete proof, and in exercise to everybody to make this a precise proof. So this means that the pentagon inside is equivalent to the exterior pentagon. So modulo projective transformations, this transformation on pentagons is actually identity map. If we take this equivalence into the account. Well, so this result, so Richard Schwartz, who started to think of this, what I'm going to talk about, actually he knew it from John Conway in some 1980, but the result goes perhaps to ancient Greeks. It is very old. And well, and so the picture is also well known for ages, and people associate some magic to this pentagram. And so, for instance, people associate to the vertices elements. So we have in cyclic order air, water, what else? The earth is here. Here is fire or heat, and here in Greek, ideia and spirit. Okay, well, so my talk today consists in 5 parts, and that was actually the first part, introductive part, which corresponds to the air. So, second part now. Second part is called background. And so pentagram-wise, it corresponds to the Earth, of course. Okay, so what is the problem generalizing this situation? So what we will continue, we'll consider an n-gon now in RP2 on the projective plane, not necessarily closed as here, but with some larger class of n-gon. So we call it twisted n-gon. And I give now the definition. So a twisted n-gon is a map phi from Z to RP2, and with 2 properties. first of all, it is almost periodic. So for every I, phi I plus n equals m phi I, where m is a fixed element of PGL 3 called monodromy, the monodromy. For instance, if M is the identity, then we get a closed n-gon. And second condition, I just some non-degenerescence condition. I don't want 3 consecutive points to belong to the same straight line. Okay, so forbidden something like that. Okay, so this is the first condition, and this is the second condition. Okay. So let me call P capital N the space of all of twisted n-gons modulo projective transformation. Okay, now we define a map on this space. Well, of course, the definition is simply repeats what we had for the pentagon. So we consider the shortest diagonals joining point number I with I plus 2. And what we get is another n-gon, another twisted n-gon. Okay, so we have a map on this space. Well, and so I'm going, what the theorem of our work with Tabachnikov and Schwarz is that this map is integrable
Just explain to us the identity map.
Oh yeah. So yes, good point. So yeah. So I will finish first this theorem. So it is integrable, and well, since we are not experts in discrete integrable systems, I'm sorry to say, so we understand integrability in only one sense, means Liouville integrable. Liouville-Arnold, some people say, in the sense of, this means there is a Poisson bracket preserved by the map T and sufficiently many first integrals in involution. So we will see all this. So a good point.
Are levels compact?
Sometimes, so we have a Lagrange fibration, and sometimes we can prove the fibers are compact for some classes of n-gons with some convexity condition, additional condition. In general, they are not compact. These Lagrange leaves of this formulation.
For monodromy equal to 1.
Well,
Identical map.
yes, it is also a very good point. So unfortunately, we cannot say so T restricted to the closed n-gons is integrable, because this Lagrange foliation has singularity exactly at the point. So the more degenerate M, the monodromy is, the more Lagrange formulation is singular on it. So this is still a challenging problem. We don't know how to succeed in this case. So if we wish to consider the most geometrically natural situation of closed angles, we cannot say anything or almost anything in this case. So it is integrable for generic leaves, for generic M.
Singular means that tori are even has less dimension than like in identity.
Maybe some before.
It might be even over integrable.
Perhaps some
more integral than.
No, I don't think so. So actually, degenerate means that the differentials of our first integrals in involution, the differentials are not independent anymore on this identity.
So you might.
So it can be some bifurcations or whatever one can imagine. So it's no more tori, but some complicated Lagrange, singular Lagrange manifolds.
This partial equilibrium. Think of the harmonic oscillator. You know,
Yeah.
you can take.
Well, it's many good questions could be asked. Yes, we don't know. We have not investigated this. If it can be viewed as an equilibrium, this identical monodromy. Yes, of course, it's a good question. Well, just to say an example. So we somehow would like to understand this theorem as generalization of this classical result. So indeed, here, if we consider T and restrict it to the space of Pn with identity, just the forbidden somehow case, then of course this is an identical map. So this is a starting point. Well, so the short story of this problem. So Richard Schwartz, who is a geometer in the sense of almost lost nowadays. So he considered for many years, 20 years, this pentagram map, and he created a program on his computer, and the program indicated some periodicity or quasi-periodicity of this map. So it was a natural conjecture. He conjectured the integrability, and well, so this is an attempt to answer this question. Okay, so very well. Now, so what are we going to do is to reformulate this a little bit, this problem in more algebraic way. So let us forget for a couple of minutes, forget completely this, what I said, and let me consider the space of linear difference operators of the following form. A very standard problem. So, well, Vi is a sequence of numbers, and so we assume AI and BI to be n-periodic. So these are two n-periodic sequences. Very good. So just I take the space of all these linear operators. Well, as I ask the question number 3, what are these two spaces, the space Pn and the space of these operators, are in common? once again the same question. So obviously the answer is they are the same. So put it here. So a kind of trivial statement is that the space of all linear operators, difference operators.
Linear equations, yes, yes. You have no spectral parameters.
Yeah.
Not operator, but linear equations.
Linear equations, yes. Provided here, however, important thing, provided, so it is the same space. It is the two spaces are isomorphic, provided n is not a multiple of 3. Yeah, so this space of equations is the same as the space of twisted n-gons, modulo projective transformation. Well, well, I not give here a proof, of course, but the comment how to understand this isomorphism. Well, if you have an n-gon in RP2, then we can try to lift it into R3. So we can try to lift in some way to R3. Well, there are, of course, many ways to do this, but what can we say? So remember this condition that no 3 points, three consecutive points are on the same line. This means that 3 vectors vi, vi plus 1, vi plus 2 are linearly independent. Therefore, if you just take the next one, vi plus 3, it will be a linear combination of these 3 vectors with arbitrary coefficients a, b, and c, I. However, so there is a way to lift this n-gon to R3 some normalized way. So we fix the discrete Vronsky operator be constant, say 1, for all i's. And it is very easy to prove that if under this condition there is a unique way to lift the space of n-gons with this condition, and then immediately this is equivalent. It is equivalent, very simple calculation, that to this coefficient is 1. Okay? Well, so this is more or less the proof of the statement. Well, actually, it is trivial, and the statement is very standard observation in some projective geometry, projective differential. Okay, so we proved nothing, but still we have a corollary here.
So I'm so confused what your space of linear difference operators acts on. Are you acting on 3 component vectors?
Well, yeah, sorry, I'm sorry. So I'm trying to save time, but actually I may even do worse. So, of course, so a solution, as I told, is a sequence of numbers. But there are 3 linearly independent solutions. So we can put them together and consider V as a 3 vector. Right? And so, for instance, we can fix some initial conditions And then, so this solution is three-dimensional. The space of solutions.
It is scalar operator of third order.
Yeah,
If
sure.
You have three, but it's
Three
not
independent
better.
solutions. So we can,
Scalar operators.
yeah. So we can put them together and consider as three vectors. So in this sense, yeah. And this, by the way, will gives us the way to understand. So we given a.
So the V's in the two.
Yes. So
backwards
yes,
are
I
the
explained. By the way, I explained how to write down the equation starting from the n-gon, but in the opposite way. Given an equation, choose three independent solutions, put them together, and then project.
Yeah, so the V on the lower blackboard is another object than one on the upper one. That's what you're saying. Because on the upper one you have scalar equation, but
Yeah.
you take three solutions. And then
Yes,
you put down
yes,
the
yes.
lower
Thank you. Yeah, yes, exactly.
So another triple of solutions differs by SL pre-R by single, yes?
Yes, exactly. So if we change the three solutions
Okay,
at the beginning, then we obtain equivalent n-gon.
yes.
Projective equivalent. Yeah. Okay. So, well, actually, we have a corollary that saying that this space Pn is topologically trivial, isomorphic to Rn. Well, of course, always in this situation, because this difference equation makes sense for arbitrary periodic sequence of A's and B's. It is very interesting question to understand what is wrong in the case when n is equal to 3m. So actually we suppose, but we cannot prove it. I don't know, maybe somebody knows, that in this case there is some non-trivial topology in the space of twisted n-gons. Okay. Well, so what is good in this way to represent our space is that we obtain the system, global system of coordinates, A and B, and everything can be calculated in these coordinates. So, first of all, so we have an explicit formula for the pentagram map.
Darbuka order. Darbuka order.
No, in this AB coordinates, I mean.
Are they Darbuka order?
Not exactly, almost. Yeah, we will see. Yeah, we will see. We will see actually. Yeah. So let me take linear functions on the space now. So linear coordinates AI, BI, and apply our map T. So on these functions to pull back, if you prefer. And the formula is, well, I find it beautiful combinatorial expression. Here we have a product. I write it down explicitly because I think it is sufficiently beautiful to be times B So what is M actually? So this formula, well, the similar for B. So this formula is true if n our number of vertices, n is equal to 3m plus 1 or 3m plus 2.
How again was T defined? Can you remind me?
Sorry?
How was T defined again?
Oh, so T is a pentagram map.
Ah. And now for the n-gon.
Yeah,
right?
and so, well, I didn't say, but of course T is defined on the space Pn because it commutes with the action of, it is projectively natural, so it commutes with the action of the projective group. Good. Okay. Well, a hint how to obtain this kind of expressions, this formula, and also a few words of the geometric nature of this map T. Actually, everything comes from the projective duality. So unfortunately, we are still in part number 2 of my talk. So we need to introduce the projective duality, the notion of projective duality. Okay, so, well, we live in the projective plane, RP2. Its dual, which is, of course, isomorphic, again, to RP2, is the space of straight lines. Okay, so if we have a smooth curve first, if we have a smooth curve here, something like that, gamma, then gamma dual, what is gamma dual? The duality is simply given by the tangent line. So this is gamma dual, the evolution of the tangent line, viewed as a curve in the dual space. Okay, so the situation is very clear for smooth curves. Now, we don't have a smooth curve, we have an n-gon here, broken line. So what should be understood as duality? For instance, if we take vertex a plus 1, a plus 2, what is dual for I? Well, what I was going to say, there are at least 2 natural candidates, maybe more. I can call this as dual. So, well, this is vertex number I, so Vi. Say this will be Vi dual, this line. Why not? Well, I call this map, this is the duality which sends P n-gon in RP2 into the dual space, and I call it alpha. And this is the definition. But there is another candidate. So this will be, well, it's not, this is alpha of Vi, okay? This line. Well, another natural candidate the definition will be even more symmetric in this case. Why don't we take this diagonal? So this will be called beta of Vi. And I have actually another map, so I have 2 maps, alpha and beta. Now, very simple statement, lemma. T is a combination, a composition of alpha and beta. So T is a composition of 2 natural projective dualities. First we go to the dual space, and then we come back. We send it by beta, and we come back by alpha. And so we found ourselves in the same plane here. So this is a very simple but nice geometric statement. Indeed, so let me draw picture here. This is vertex number I. So first I apply beta, and then I apply alpha. When I apply when we want to go back, so here we have to draw straight lines through 2 points, and to go back we have to cross 2 lines. Okay, so first I take beta of vi plus 1 and beta of vi, and then to go back I have to cross 2 consecutive lines, and this gives me this point. So this is a proof. Very good. So actually this helps us to calculate explicitly the map T, because we can calculate the formulas of alpha and beta. I don't in terms of the coefficients A and B, so I don't give explicit formulas now, but okay. Well, so we should continue with the next step. So pentagram wise, the third part of my talk is called, oops, sorry. What is hot? So till now we just consider some well, beautiful geometric map, but with no relation to any known integrable system, and somehow. So the statement is that the map T in the continuous limit that n goes to infinity when we approximate our n-gons by smooth curve is nothing else but the classic Boussinesq equation. So let me explain how we obtain Boussinesq from the pentagram. So instead of n-gon, we have a smooth curve now, smooth parametrized curve, gamma of x. Let me take an arbitrary point, so gamma of some particular value of x. Then I take small epsilon, x plus epsilon, x minus epsilon. Of course, I assume that, well, the same condition, this condition of non-degeneracy gives us that gamma is non-degenerate curve. Gamma prime and gamma second prime are not collinear, linearly independent. Span the tangent plane. Okay. Well, so now we can draw straight line here, and then we take envelope, the envelope of all these lines, and we get a curve that I call gamma epsilon of x. Of course, then epsilon tends to 0 in this. Epsilon tends to 0, and so this is an analog of pentagram map. It becomes a vector field on the infinite dimensional space of curves. again, if we have a geometric situation, we can reformulate it in an algebraic way. Instead of difference equations, we get here differential equations of order 3. So the space of non-degenerate curves is isomorphic to the space of linear differential equations of order 3, or if you prefer differential operators, let us say of this form. So this is precisely analog of what I told in the discrete case. And of course, this is also a very, very, very common situation. So this operator is of this form, but I prefer to write it a little bit in more symmetric way. So of course, W is equal to V minus U prime over 2. Okay, so I put 1/2. Okay, if you agree, so this is a more symmetric way to write this equation. So statement that the map T becomes the following differential equation on U and V. So these are our coordinates now. U and W, okay. U and W. So, well, in order not to write wrong things. So, W prime. Here we have minus U prime over 3. It is quite a calculation, by the way. It's a very tedious and long calculation. And so this is precisely the most classical way to write Boussinesq equation. Very good. So, well, what I say, what is hot? Because actually this is, of course, the active. This means that
It's like we write Boussinesq in form of solitary theory, like from KP. Yes,
Yeah.
but in traditional Boussinesq we write it in different form. But we are not the same, but equivalent. On physical level. It is KP form. So you obviously see KdV part and right hand. It's already taken from solitary theory.
I think I've
It's
seen
KP
precisely.
form.
Okay.
After the Kharab-Shabat.
Okay. Okay, thank you.
Boussinesq is written in classical literature a little bit different. It's not the same equation, but they physically equivalent, taking something small, something big.
Okay.
I just.
Okay. Well, but so this observation tells us that this pentagram map is nothing but a discrete version of the Boussinesq equation. So this is, of course, a very active subject, and so Frank is an expert, and I would like to know more about the difference and to the maybe
is this
some.
just new result that pentagram is some X discretization of Boussinesq?
Yes, it is. It is a discretization.
Yes,
it is.
It was not discretized before. Yes?
It was.
Boussinesq.
It
No,
was.
there is
Frank.
both. Frank did it.
Yes, Frank did it.
And you observe that it is pentagram?
No, this we
no.
didn't know. This
No.
this is-
So yeah. So this is, of course. So this is why I would like to ask a question: what is in common? And the answer, I don't know. Okay, maybe it's the same. Maybe not. Okay. So, but at least so we understand now. This pentagram map is a discrete version of the Boussinesq. Very good. So, pentagram-wise, so the next part is water. And so my part number 4 is the Poisson bracket. This is perhaps the most important part of my talk. To prove integrability, we need the Poisson bracket. Okay, so
Poisson, because Poisson is fish, fish and water.
yes.
You see, I also discovered already not being young, but many English and French names mean something.
Also, this naturally corresponds to the pentagram. Okay, so the Poisson bracket, there are, of course, many different ways to write explicit formulas for the Poisson map. So I prefer the simplest, for me at least, the simplest way is just to give the brackets between the coordinate functions, and then we can extend it to any other rational or smooth functions. Okay, so it is sufficient to say what is the bracket of between all a's and all b's. So first, let us take a and b. Poisson bracket. So this is a definition. Actually, the definition first. First, I give the definition, then I prove or announce some result about it. Well, so here we get 0. So it's already a good way to start. Now, the bracket between AI, AJ will be proportional to AI, AJ with some coefficient, numeric coefficient, which is actually a sum from 1 to m, again, the same kind of summation, delta I j plus 3k minus delta I j minus 3k. So we have this cyclic sum, and it is in some sense non-local expression here, because we have to go all around the vertices to. So example, yes. So sorry, and the bracket between b's is precisely the same, but with opposite sign. Exactly the same, but with opposite sign. So just an example, to give a couple of examples. Let us take the first non-trivial case, n equals 4. So it is a pentagram map, but with only 4 vertices. But it makes sense because this quadrilateral is not closed. Well, then we have 4 coordinates. Let's say A1, A2, A3, A4. And so we see that they are related in this way. This is the formula. And this arrow direction means the plus or minus sign. Okay, well, another example, n equals 5. We have 5 coordinates A and 5 coordinates B, of course. And here we obtain the pentagram, of course. What else? Very good. Okay, so a very simple statement is that the important statement is that this bracket is preserved by the pentagram map. So T preserves this bracket. So I would just.
Casimirs staying.
So T.
Casimirs are they?
Yes. So first, okay. So it is T invariant.
Invariant, yes.
Okay, and what about Casimirs? if n is odd, then there is only one Casimir function. Then the bracket between a's has a corank 1, only one, and the Casimir function is multiplication of all a's. A1, A2, so on, an. If n is even, I don't say, but the same thing with b, of course. So it is actually corank 2 if we count. Yeah. So if n is even, then the bracket between a's has two Casimir, independent Casimir functions. It has corank 2. So we have two Casimir.
Two Casimirs in every sector.
Yeah. In
sectors.
A, 2 in A and 2 in B. Yeah. So what are they? Actually, it is all odd, A1, A3, A5, and all even, A2, A4, so on. We have two Casimirs. So otherwise, it is symplectic. So we can see that for on the level when the Casimirs are different from 0, we have something smooth symplectic manifold, submanifold of R2n, right? Okay, very good. So now
it responds to some, I would say, traditional soliton type bracket in Frank's work, because you probably constructed something like that for discretization. And Hamiltonian, you studied Hamiltonian, should be some operator treatment of coefficients.
Hamiltonian
Like
is
in
not
Laxter,
symmetric.
yes.
Yeah.
That's
Hamiltonian-
coefficients, that's probably some coefficients of
Poisson structure,
operator.
yes. Yeah.
Poisson structure, this corresponds to.
Probably,
Is
yeah.
it same corresponds to, or there is some sort of Leonard-Magre phenomenon with two brackets here?
Kind of what we're
Well,
trying to.
Or it is unique?
Yeah.
Unique.
yes, sure. So let me explain. So let me explain a little bit. So the origin of this Poisson bracket. Sorry.
Does not.
I keep the bracket, but I erased here.
Exactly.
So this Poisson bracket, this Poisson bracket is the discretization with S, right? Of the very well-known Poisson bracket for the Boussinesq equation. So the so-called first, this is the most elementary, the first.
So still there is a pencil of brackets here.
Hmm?
You claim that there is a pencil of brackets here.
This is precisely what Ian is investigating. So this is precisely what Ian is investigating. So we hope there is a pencil in this discrete case, as exactly as in the
Normally, if you have two different brackets, they form.
well, yeah, but discretization is somehow an art. Can be done in different ways. So it's not very elementary to write down the pencil of compatible brackets here. But so this is discretization. So what we do in this procedure allows us to pull back the simple natural bracket for Boussinesq. Okay, so the last point of my talk, the last point here is, of course, the commuting first integrals in involution, commuting invariants. And so, well, the construction is as follows. In integrable systems, very often, one can obtain first integrals of integrable systems from some monodromy. And so here we will have monodromy invariants. So unfortunately, I erased the equation that you remember, this linear equation. And since AI and BI, the coordinates are periodic, of course, there is a monodromy acting on the space of solutions, right? This operator of monodromy is simply an element of PGL3, of course, of SL3, dependent on A and B as a very complicated polynomial matrix with polynomial entries. Okay? So what about those? Of course, it is preserved by the pentagram map. So, and if we take the trace of monodromy, it will be a very complicated polynomial preserved by the pentagram map, but only one. So what should we do with this polynomial? And the answer is as follows. So there is a simple procedure of rescaling. Can you see this? No, maybe not. But why don't I put it here? So actually we can rescale our coefficients. We just take AI, BI, and we multiply by a parameter t here, and we do multiply 1 over t here. A kind of rescaling. Obviously, this commutes with t. The pentagram map, it commutes with t. Why? Because we have an explicit formula that unfortunately I erased already. So the coordinates behave as follows. And here we have 1 plus some A, some B, 1 plus some A, some B. So this commutes with rescaling. The same, similar for B. Okay, well, this was a product of that. Okay, so this we can immediately get from the explicit formula. And now, if we put the parameter t here if we put it into monodromy, then it will be a sum of homogeneous in T polynomials. And this gives us exactly the right number of invariant functions. Then we give a separate proof that all the Poisson brackets of these functions vanish. And this is the end of my story. So we would probably like to discuss the spirit point, but as usual, there is no time to take care of spirit. So I stop here.
You need more dimensions to fit the spirit.
Okay. So
Any questions? Yeah, I have a question for your formula for T on AI and BI. It seems that it's a non-local formula.
no, it is not. It is not. It is non-local. Yeah, you have go all around
Yeah.
of all vertices.
You should have though some other variables where, because the construction is local.
Correct. Yes, you are right. You are right. There is another system of coordinates in which the T map as well as the Poisson bracket become local. So this is another coordinate system, quite easy to define. It has some advantages to calculate, for instance, but it has also some disadvantages with respect to this A and B. So yes, it's just the kind of visual coordinate system that was used by Richard Schwartz. For every vertex I, Schwartz considers 4 lines through I. Well, let us take I plus 1, I plus 2, I plus 3, together with this line. So we have 4 lines. And then she just takes the cross ratio and he calls it xi. We can do this. So this was the left, he calls it the left invariant, and we can do it in the opposite way to obtain yi, and this will give us a coordinate system. All formulas simplify in this coordinate system, but we don't see any, in this situation, we don't see any relation to Boussinesq, any relation to linear differential operators, and so on, so on. So we lose some kind of spirit advantage.
You
but
lose connection with Boussinesq.
Yeah, so we lose.
Point, yes.
Yeah, we lose idea, but we gain in some calculation. So here we can write down the
Can
formula.
you define something like analog of your T in continuum limit and calculate it in continuum Boussinesq? Analog of your non-local transformation as can be in principle. I don't know whether it can be or not.
Yeah.
And does it have any continuum limit? Some non-local continuous transformation.
But the only continuous limit I know is just the Boussinesq. So
No, it's equation. It's
Yeah.
a local part.
Yeah.
But in continuum limits, you might define some non-local transformation.
Non-local
For
transformation.
example, time shifts of different
Okay.
hierarchy systems, and even more.
Yeah, yes, true.
There exists non-local transformation.
yes, so you
in,
discretize
natural problem.
coordinate, but
Your
not
T.
time, right?
Does it have continuum limit
The thing is that T was
in terms of Boussinesq hierarchy? Yes.
Yeah, I don't know.
Or maybe symmetries which a lot of people consider symmetries
maybe the way to discover
hierarchies.
it, to do
Yes,
it.
but
Maybe the way to
should
discover
be
it-
something.
Maybe the way to discover it is just to write down what you exactly like this with the epsilon shifts and look at the affinization of this projective curve,
maybe-
which is
maybe-
exactly what you have
Maybe
there.
yes, and then don't discretize
Take the
epsilon.
limit and then
Consider it like
Yes, it might be some very
Yeah.
simple geometric
Yeah.
map, something like
worth,
a chronological
worth trying.
exponent or something like that.
maybe.
Within hierarchy should be
Yeah.
Yes.
calculated.
Okay.
Yes?
Okay. I see.
Can I ask, maybe I missed it, but in your construction, what about the spectral parameter, or is this T supposed to be?
Yes, T is probably spectral parameter. Yes? Yeah, otherwise, yes.
T.
This equation,
to understand
linear. After T, you really have operator, not linear equation. Yes, but
True.
you know that in Boussinesq we have operator.
Yeah.
Yes, exactly. You discretized, you had operator.
Yeah.
Lux pair, yes?
Yeah, but it seems that in our case,
Yes.
No,
There is.
this is-
There is. I didn't mention it, but so there is a Lux.
Which people participated? This is 1991.
There is a Lux representation of. There is a Lux also a Lux
Didn't work.
representation of
Missed
this
paper.
map T. It is worked out by Young very recently.
What was worked out by me?
Lux form of T map, Lux representation for T. Well, it is not very geometrical. This why I don't. Yes.
Yeah, my question is about what you found along the way, so to speak. This is this new integrable system. The T-map apparently led you to this Poisson bracket, but once you have this Poisson bracket and once you have these commuting quantities, you can ask, what do they look like if you go to Darboux coordinates? Is it a well-known integrable system, perhaps? Did you do this for n equal to 4, for instance?
Yeah.
But it is same discrete.
We did this for n equals 4, n equals 5.
Or it is not
7, and so
unclear.
on.
Unclear.
I suspect it's not.
We tried to recognize, but we did not.
Two different, completely integrable discretes.
If you see something in terms of x and
Everything
p's, you
might
can
be.
more easily recognize it, right?
Yeah.
The things.
Yes, I don't know how to answer. Well, in order to obtain Darboux coordinates, we should take logarithm of.
Non-linear.
Right.
Integrable discrete.
Ask for an exponential substitution, right?
Yes,
Then
yes.
probably you can simplify matters.
I don't know how to simplify this formula. Well, I have to say that we recognized some similarity with formulas suggested in a recent paper of Konopelchenko on some Menelau's theorem and integrable systems obtained from this projective as different constructions in projective differential. I don't know what if there is
some unnatural way.
intimate relation or it's just the projective geometry that provides some
If it
similar.
Vaguely reminiscent of the Neumann
doesn't
system,
mean that it is not.
which is a well-known integrable system, but you have to go to the correct coordinates to see the map, if there is one, and to see the equivalence to that well-known system.
Maybe so. We tried it for n equals 4, n equals 5, and we didn't see something that we recognize. We didn't recognize.
I mean, in Darboux coordinates, it might also be much simpler to recognize whether the flows are complete, because this is not obvious from your work at all. You're already saying the level surfaces are not compact in general, so there is a problem that you might get to infinity in finite time.
Sure.
This Poisson bracket, there was Poisson brackets in the old works 1991 concerning discretization of Boussinet. They should somehow coincide with discretization of Poisson bracket associated with third order operators. Yes.
I think.
We know that there are two brackets in operators.
Yeah.
Higher order operators. One of them is Gelfandiki bracket. The second one is
Just linear.
Adler someone.
Yeah,
That's
Adler.
another one, which is extension of lesson 2.
Yeah, so we
First
first Gelfandiki. Well,
Yes, but it was found by Adler and someone.
Sure.
I forgot this.
Sure.
This extension for corresponding second bracket.
yes. So what we discretize is this Adler bracket, but I think so. People
So it means
try
that
to
in this
discretize.
case, you naturally should have two brackets.
We should.
In continuous Boussinesque, you certainly have two brackets.
That's exactly what.
Just
That's
yes,
exactly what is perplexing us.
yes.
It's precisely the annoying thing.
And discretization should preserve
Yeah.
this picture.
But this seems to be exactly discretization of third order differential operators.
Yes,
Set up- everything should
preserving
just-
both pencil brackets.
Everything should just go through it. Unfortunately, it's not so simple. Something
Yes. Yes. So computations are in progress, but still.
Might be a non-local formula from one coordinate to another. There are not easy to see that it is in fact equivalent system.
We had a kind of classical R matrix description.
Yeah, okay. So your approach was
Which was
classical R
not
matrix,
local.
yes? Not like not like Gelfandiki and Adler brackets, yes?
Yes. But what we did, yes, it doesn't use this bi-Hamiltonian or nature, but of course, we hope that this is the case. Of course,
You even don't write it as a Lux pair with discrete third order operator. would be, I would say, natural methodological exercise to write your discrete system as a LUX type system with third order difference operator.
So Jan did this.
Well, he keeps saying
Yes.
insists on this point.
I insist that Jan
Yeah, or someone else.
have already done this, but
Maybe Jan
here
or you.
he denies. He denies.
No, just
The second
before we
part.
came in here, he said, look, that's the thing, I noticed it. But show it to Frank.
He
He'll
denies.
stamp it or not.
He denies,
Maybe
but
he
I-
won't stamp it. You know what I mean? It's,
The kind of informal discussion stage. So let's thank Valentin.